Welcome to another installment. Also, you want to be a data scientist now, HPC edition. All right. So, first of all, my name is Didier Barradas. I'm not going to use Robson. That went wrong. And here's also my colleague, Dr. Mohsin Shaik. We are part of the data science team that manage Ibex, also SHAHEIM, here in the university. All right. So, as you can see, I'm part of the visualization core lab, while Mohsin is part of the KSL, like the supercomputing lab. So, there is a bunch of us that works in the shadows for you, and this is part of the thing that we want to give you, just to know, so you know how to use Ibex a little bit better. So, of course, this is the vision and mission of the KSL. KSL is basically also, KVL is also part of the KSL, and we want to provide you with the opportunity to use the coolest machine that we have. And you know that for the news that we have an upcoming super machine coming, Shaheen 3, sorry. And for today's, we will go over this quick plan. Hopefully, we will not take too much of your time. I know you are busy with the commitment. If you got invited, lucky you. Okay. So, first of all, I must say, we have been spreading information all over the place. We have documentation, YouTube videos, YouTube channels. As a matter of fact, we have this thing called Confluence, where you can find the actual starting pack that I wrote. By the way, if you find some error, please tell me. And in the starting pack, you will find a bunch of quick links, a bunch of information that will be tips for you. More importantly for us, it will also give you the basic backbone of how to write a ticket to us. We receive a bunch of tickets from different users. They're like, I have a problem, and I am so tempted to answer, I have a giraffe. Okay? So there are some highlights there, some things that we need you, like to put in the ticket. For example, who you are, whether you're running, where are you running it, and some other details. So for today, we're going to use this GitHub repository that is all the way on the last part of this slide. And that will be our main also repository to have templates that you can use on Ibex. All right, let's start. What is KSL platforms? You know, we in this university were very lucky because we don't have just one HPC device. We have two. We have Shaheen and we have Ibex. Now, the landmark is Shaheen. This is Shaheen 2 as it is now. It is still in production. It's still working for KAUST. Several researchers use it. And it has this kind of architecture. It's super fast. And it's all CPU based. It's using this Dragonflight architecture that you can see there. It comes from a company called Cray. And it has a speed of 5.5 petaflops of second, basically, of operations. If you know what it means that you can see a lot of videos like in seconds, right? Okay. So Shaheen has a very similar system file to what we use in Ibex, but you will see the difference. For example, in Shaheen, you have your home, you have a scratch partition where everything that you compute, everything that you put through the computer should be processed. All your information should be in Scratch. Projects is something special for each of you, each of the users. You can save data there, something that is important, but you cannot process the data there. And there is another partition called the box buffer, which is important because it's a special partition that will allow you to do supercomputing even faster. But that's basically on demand. Now, it has another kind of different policies. For example, the projects, it will purge every 6 months. What does that mean? If you didn't touch your file in 6 months, it's gone. You cannot recover it. And in Scratch, it's even more strict because it's like in 60 days, if you haven't touched one of your files, it's also gone. It's going to be removed from the system, meaning basically erased. So please, if you're working on Shaheen, Don't leave things to scratch. Do a regular backup. And you have that right to do that. So please keep in mind that these policies are enforced. Now, Ibex. What is Ibex? Why do we have two things? Why do we have Ibex? Why do we have SHAHEIM? Well, the easy answer for Ibex is like we have so many different high performance computing nodes around the university. They were unified and Ibex is born. From my point of view, what I call a Beowulf cluster because it has different architectures inside. This is the first difference with SHAHEIM. SHAHEIM is all the same architecture, all the same CPUs, all the same connections, and everything is homogeneous. Ibex is not. Ibex has concept of one type of computer, different types of CPU, different type of GPUs, basically kind of a Frankenstein. Okay? So it can be connected to SHAHEIM, but it has also a different kind of organization. You can see we have Intel nodes, AMD nodes, some large memory nodes. That doesn't have that doesn't exist in SHAHEIM. Okay. So the CPU nodes of Ibex, they come in different forms with different memories. Why do we need some nodes that is large memory nodes? Some applications, usually for informatics, it's all the memory that you can give them. So there are a few CPU cores there, but you can allocate a lot of memory. Those are not connected to the GPUs, if you were wondering. These are CPU only, and they only run CPU processes. Okay. And then you have the other ones, Skylake, Cascade Lake, and Run, that depending on your needs, if you need, like, for example, the AMD specific architecture, you can access them. Or if you need Intel, basically, if you care about what you need, you can specify it, and we have it for you. Okay, now the GPU nodes that everybody is using nowadays because AI, right? So if you want to ride the wave of AI things that are happening now, you need to know what is a GPU first. And here's a list of what you have available here in Ibex. Like I told you, Ibex is basically a Frankenstein. So we have, for example, still P100s and P6000, which you can say in the timeline of the GPUs, these are grandpas, but still working. And they still can actually load things for you, and you can use them to basically do a small prototype of everything, of anything. Then we have the GTX, the RTX, which are more new, and in these last 4 months, we have the most new ones that we have, the B100s and the A100s. Now, the B100s, we have 2 types of those. You can see them here, the difference that they have. And you can see also that there is a very important difference, the NVLink. For those of you that doesn't know, NVLink is a technology that connects the NVIDIA GPUs specifically to communicate with GPUs. This was not something that they come up from the beginning. They came up with that after they saw that the GPU was important for computing. So A100s and B100s, this is why they are faster than their predecessors. One of the reasons. Okay, so you have different memory, you have 32 gigabytes, you have 80 gigabytes, and you should also know that these are very, what's the word? People ask for them a lot, so they are very coveted. So taking that into account, like you will not ask for a B100 and get a B100 right away, sometimes because many people need to use them. Anyway, that's the other thing. These resources are shared. They are not your personal computers. So you have to be patient sometimes. Okay, file systems. This is, like I told you, similar to SHAHEIM. You have your home directory. Now, your home directory, as you can see in this slide, is very small, 200 gigabytes. All the computers that you have here has more than that, way more than that. So home is basically just to keep very small things that you deem really, really important, like configuration files. or very small scripts. You cannot put databases there, obviously. Then we have the /ibex/user, your name of user, space. That one has 1.5 terabytes. That's the equivalent of the scratch in Shaheen. This is where all the computing has to happen. This is where you want to work. One, because it has a lot more space. Second, because it is actually connected to something that is called Wilka.io, which allows to be compute in a shorter manner. So this is a difference also with Shaheen. Shaheen doesn't have Wilka.io system. So believe me, it's faster for the moment. Okay. Now, the node local storage is something that is basically, I think, is a computational trick that if you run a process and it allocates in the memory of the node, it will live through the life of the process you're throwing out. Meaning, you run a program, it can access that memory, but then when the job is done, that goes away. Okay? This is the three types of file system you can access on Ibex. All right. Let's go over here. So, because we have two different supercomputers and these are two different types of users, Shaheen is open to the outside, meaning that the resource is available for the kingdom, but Ibex is only available for people in KAUST. So, for example, if you want to access Shaheen, you have to submit a proposal. And there are two types of proposal, development projects and production projects. Okay, you can ask for 2 million hours in a development project, and you probably will get granted because it's one of those projects where like I need to tinker with my code until it's really and fine, and I'm happy with the result. And then production project, I'm going to run the program without change just to generate all the data, and then I will analyze it another way. In Ibex, you just need to be part of KAUST. So congratulations. You already have access to this if you are in KAUST. Okay. One of the things that you have to do now that is new is that you have to nominate your PI. This link here, every time that there is somebody new coming to your group, please tell them that they have to go over this site and nominate a PI. They have to be part of one team so we can control who is doing what. Because obviously we have to know what are you doing and if you're using correctly the machine. Now, log a ticket. You can actually use this. Look here. This email direction to contact us. Usually, if you have a problem, if Shaheen is slow or Ibex has some problem or you have some question, you can also reach us through there. You can reach us through Slack. There is many ways you can reach us, but you can use pretty much this one for any general purpose that you need. Okay, so a very non-so-discussed concept. What is an HPC cluster? You probably know somebody who is running things on the login node. Why? Because many people come and they don't know what an HPC cluster is or looks like or what is it. So many of us are just used to use our computers. It's like my computer, my work, I do it whatever I want, and I put it wherever I want. This is not the case for HPC clusters. This is not the case for any HPC cluster. So you have a login node, which is here well, you can already see it, right? You connect to the login node using a terminal, usually, depending the program, but let's say it is a terminal. And the login node is just the opening door to a very first room that you are going to step in. I know some beginners think that if you enter a login node, you're entering a complete different room. And if you use another login node, you're using another room. This is not the case. The login node is one room where you enter just to look at the supercomputer. That means that if you execute anything in the login node, you're not doing supercomputing. You're not using the full power of the cluster. So what is important is that the login node will actually let you, through a language, tell the system, hey, I want to do supercomputing. So I need to access the parallel system, which is all the CPUs we have, and the compute nodes that communicate with that parallel system that is storage. And then these two are connected through special cables that is actual supercomputing. This is the part that you're interested in. You want to explore this. We have many new users come and try to do things in the loading node. That's not the supercomputer. It's just a waiting room. Okay? So explain that to whoever comes to your group next, because believe me, there is a lot of beginners that comes and they don't know that they're not using the supercomputing. So it's an important thing that you have to spread around. The loading node is not a supercomputer, it's just a power to the supercomputer. Okay. Why I'm telling you this? Because this happens. The loading node is a resource for everybody, right? It's where you basically search through the files, you go over, you basically think about it as a very crowded thing. This here is the worst case scenario. This was one user. Only one user was watching this. You see the red box there? It was using all the resources for everybody on Ibex. It was running Mathematica, one software, in all the loading nodes. That means that if I want to do an LS, CD, or I just want to navigate where my data is, I could not. It will take forever because he's using all the resources. Imagine like a big balloon filling up all this space, and then we cannot move. This is basically it. Okay? So again, in the loading node, don't do anything. Second of all, you are writing the loading node to your home directory. Your home directory, as I already said, it has 200 gigabytes only, and is not connected to the supercomputer. You're not doing supercomputing if you're doing things there. Please know that as it's there. All right? Okay, so let's start. We have, as a matter of fact, 3 logging nodes. We have a GPU logging node, a CPU logging node, and now a VS Code logging node. Why we have a VS Code logging node? Because it's a very popular GUI that everybody started using, but it was generating so much metadata that we had to basically isolate it in order to not cause problems like the one we see before. Okay? So if you're going to use VS Code, you can use this one. If you're going to use, or you're only interested in the CPU, let's use the one in the middle. And if you're interested in the G logging, the G logging is the one that we're going to use today. So go ahead, please. Try to log in. If you already know how to log in, go ahead and execute these kind of commands. As you might know, yes. Yes, this is just giving you the very first waiting room. You're just accessing to your home directory, and that's it. As a matter of fact, that's something that people usually doesn't understand. Like you're accessing the first room. You're not accessing still the logging node, the compute node. I will show how to do that with the VS Code open source version, which is Code Server. But go ahead, type, for example, who am I, and resolve your question of the ages. It will tell you who you are. Because all of these commands are shell commands that will help you basically to understand what's going on. One of my favorites is actually module AB. Let's do that, for example, with my own session over here. So if I go to the GPU partition, okay, let's blow this up. Everybody can see. Big enough, right? So who am I? Because I'm in a crisis. Who is my PI? I have assigned my PI. Who am I? where am I? In working directory. Now, the one that is very, very important, I think, module AB. And here we have all the different software that is installed inside Ibex that you can explore, and much more. Now, for example, VS Code question, right? You have your VS Code, you have your Remote Explorer here. I have done this so many times, and I have it already saved here. So what I do here, I will not show the configuration, but it will ask me again for my password. Many times probably. Opening remote. Okay. When that is happening, there is a bunch of things that you can do. So for example, again, this is my home. You can see all my different files here. And then you can navigate to Ibex user. In this case, if you do $user, it will take you to your space. And here I have another bunch of different files. Okay. Taking a lot of time. Let's go back. Open this one. Okay. So here, VS Code is actually allowing me to see already the data that I have in some folder. I can navigate through it. If we go and we say terminal, a new terminal, you can see here, this is a login node, the VS Code login node. Okay. So far, I'm still doing nothing. But it already put me on my folder inside of my Weka partition. Okay. So far, so good. Everybody could log in. Okay. Easy peasy, yes. With the terminal? Okay, that's French. Usually, yeah. Okay. Oh, while they check there, let's go quickly over. I think that you might be actually interested. On Ibex, we do have reference folders for datasets that are very used or used often. Like in this case, I'm showing the AI reference. The other people can also have the reference folders here. If you go to /AI/reference, you will find all of these guys. Because all the people from AI are working with these datasets. So if you have a dataset that you're interested in and your group is going to work with it, you can raise a ticket and ask us, hey, can you put this in the reference? Because it's like my group is going to be working with this all the time. Okay? And well, you have here a very small summary of what you have available for you. The home user, we already discussed it 3 times. The Ibex user is going to be the similar to Scratch user over there in Shaheen. Projects, this one is a special kind of folder that you can ask, because let's say you're going to work in a group of 2 or 3 people, and your PI literally needs to access the data too, and it's like you're 3 people working in a very specific project, and it needs a bigger capacity than 1.5 terabytes. You can ask for that in a ticket, like, hey, can you give us a folder with this amount of data, this amount of space, please? And allow these users to access that folder. And it will resolve a lot of issues because usually you have some people coming and going in KAUST, and it's like, okay, put the data there. And then it will be shared with everybody in the group. It's something that I think is a good practice to have. Okay. And of course, the references. You can go over all the references that you will have there into Ibex/AI if you are interested on it. Yes. Okay, the question was if the folders in Ibex have a policy that will purge just like this, just like in the case of Shaheen. No, they don't have a policy yet. As we grow in size and if we grow in people, and the more people, the more data, it will come a time that they will enforce a policy. Right now, there isn't. It's just about the limit, the space that you have. However, I should be very clear. Scratch and /user are not backed up. Okay? Whatever is there, if you lose it, is gone. So make backups. The only part of both computers that is backed up is home. But home is only 200 gigabytes. Yeah, that happened to Shaheen a couple of days ago. They moved the directions of the login nodes. Yeah. Yes, please. As a matter of fact, good question. When you log into VS Code, I didn't know this, but it's CPU. What you will see with the what you will see is if you do module AB, what it will load is the Rocky 9 Linux is an operating system. C stands for CPU. Okay. Now there is a trick to this. If you go all the way down to this list, it will take a little bit of time. Model AB Air 9. This is another trick. If you're looking for some software inside Ibex, you can do model AB and a couple of characters. It will return the list of those matching characters. So we recently upgraded the OS of Ibex. It came from CentOS OS, which is now deprecated, to Rocky Linux 9. With that also came this nice list. And now you can access to the GPU and CPU software stack, meaning the program that is installed either for CPU or GPU. If you want to check what is in the GPU, in the CPU stack, you can load this. But like the question here, my friend, in VS Code, you automatically load this one. If you load this one, model load, now you have all the software that is compiled for the GPUs available to you. For example, my friend, the machine learning module. Okay. This is, for example, one of the software that is installed only on the GPU stack. But in this way, it doesn't matter. You can access both of those stacks if you need them for any reason. Okay. Well, yeah. This is going to give you 9 minutes. I know because it's a very hard concept, the job scheduler. Different systems have different job schedulers. Okay, what is a job scheduler? We have something in Ibex called Slurm. A Slurm basically is the way you're going to communicate to give the directions of the resources you want. So Slurm is the way you're going to tell computer, give me a CPU that is Intel for 10 minutes with 100 memory and call my job, I don't know, dynamic. Literally, you can do all of that with a very long list of hashtag/s match. You will see what I mean. But this is a way, a very standardized way across the world of how you ask resources for an HPC cluster. Okay? It's not that difficult, but it's a concept that nobody uses outside HPC. So it becomes really mind-boggling, like, why do I have to do this in order to get just something simple running? Turns out this is the way, and we don't want to go to the dark side. In that case, just stick to Slurm. It's not that difficult, and as a matter of fact, we have a tool that will help you to deal with this. So, where the resource system? Once you're inside of your terminal, you can type, for example, ginfo -d. Go ahead, do it. It should return something like this, which is a list of the GPUs. Sorry, if you're in the glogin node, you can do this, and it will give you back the list of the GPUs. How many are they used now? How many are they idle? If they are in drain state, which means they are basically doing nothing and waiting for nothing, just like stuck. So sometimes we do have tickets from the users saying like, hey, there are some drain nodes. Can you undrain them? And then become available again. Now, one that is my favorite, like, how do I know if my job, what I put inside of Ibex is running right now, and what else is going on, right? So you can use SQ. SQ will, if you just type SQ, it will be not good. Why? Let's go SQ here. Because this returns every single one of the jobs running for Ibex right now. Not only yours, like everybody. Now, we simplify this here in Ibex. If you do SQ-me, it will tell you your jobs, only yours. Okay? You can use also -u user. It's the same thing. Okay? This is what I put here in this slide. A couple of examples that I think are very useful. If you use -u, you have your username. If you use -p, it will show a specific partition. Sometimes you are running something in a very specific folder. -j, your job ID. If whenever you know the job ID that you have in this column, you can always check it out like this. These all will give you the same result. Give you a table like this, and it will say like, okay, it's in the partition batch, the partition above, or whatever, and the name that you want to have it, the user, could be Bob, could be Joe, could be Jane, the time that is in running, the nodes, and the list of type of nodes. Okay? You will, the SQ-me, I think, is the most useful one and the quickest one because it's very easy to remember. Okay, so another thing, if you do not know what's the relationship between a GPU and a CPU and what they are doing, what's the constraints, let's say the specifications, you can do sinfo. Specifically, this sinfo -ne, and it will give you, for example, I asked for the V100 things. So for V100, we have all these combinations. You can see that it's pretty much repetitive in many of the columns because they have basically the same details, right? A certain amount of memory. They have some kind of date where they were added. And this is the CPU that they are running with. So it's information that you can just snipe from your terminal. Now, how do we specify resources? Why? What do I have to really specify for? What's the minimum that I require? Well, you need to know if you want CPUs, how much memory, how much local disks do you have. Very normal problem that we have. It's like, hey, I run a job and I don't see my results. It's like, probably because you fill your quota. It's very, very, very common that many people fill the 1.5 terabytes, or even worse, they are running things on or saving things on home, and they just run out of 200 gigabits. And the work time, that's another one. The more time you ask for the computer, the lower you are in the priority of the list of users. Because you are asking for a node for 72 hours, and somebody else is asking for one node for 5 minutes. Who should you serve first? Okay. So for that, you have two modes. Something that's called batch mode, which is basically I'm writing a script. Another thing that is called the interactive session. Interactive sessions are really good to get like in one line, usually your requirements, and it's to prototype very quickly. Usually it's enough for you to run many of the jobs that you need. The batch mode is usually to just run all that you need during hours and hours and hours, and you know it's not going to fail in theory, in shadow. So in a job script for a batch mode, you have to specify things like this. So you have your job name. Usually you can choose not to put a name if it really doesn't matter to you. Sometimes it does. Then you have your number of tasks, your CPUs, your GPUs per node. Not all the nodes have the same number of GPUs. Then all the CPU nodes have the same number of CPUs, and so on and so forth. But this is the thing that I was mentioned, that this is the way you communicate with the computer. The hashtag SBatch is what Slurm recognizes and says like, okay, so you want, I don't know, 5 minutes? Okay, I will allocate this job for 5 minutes. And so on. Okay, then we have something that is very simple. What you're going to load, the basic structure of your software that you need. In this case, we are loading the machine learning module. This is basically the software you need. Okay, or you can sort your code environment, or you can ask for some specific part of the software that you want to run. And of course, later, And of course, later you say like, okay, I want to do an SRun and then get this thing here running. This is my actual program running. Okay, don't worry, you will see this is usually a thing that you do once. It's a one-shot thing, most of the time. And then in order to tell finally the computer like, this is my job specifications and put it onto the queue, you need SBatch. So another way is the interactive way. There is one way that is called SLOC. This, in different to the other thing, will give you access directly to the compute node. You will be working like if you are working on your computer right now. Okay? This is the interactive part. And one of the ways to improve that is with SLOC. The other way is SRun. But as you can see here, once you are inside of the compute node, it's like you're inside of your computer, so you can start working just like you regularly do. This is something that I really like, usually because it's intuitive. You're already inside what you need, just go and write. And then fail as much and fail fast, because this is the way you get to the final product, right? Okay. So there is a direct way to do that, which is also SRun. The difference between SRun and SLOC is like if SRun dies, the whole job dies. If you put SLOC continues, even if you exit, and then you can go in again. So basically one is immortal and one is not. This one is more easy to remember. And I like this because it's just like, if it dies, the job dies and that's it. But it depends on what you're doing and what are your needs. And finally, this is a very good one. It's like always stop things that I don't use, and then you do S cancel. Usually, there is two ways. You can do S cancel the number of the job that you want to cancel, or if you do S cancel minus your username, you will cancel all of them because it's like cancel all the jobs under my name. Okay, so exercise 2. If you're not still in the DS training, you can start by that first point. Write to Ibex at hpc.edu and ask to be added to the reservation. We will see. So what I want you to do is go into your user space, do Git Clone, this thing here, Git code KAUST RTCL science onboarding.git. And then inside of that folder that you're going to clone, you can go all the way to JavaScript templates. And then you will do fbatch basics learn. Okay? Yep. Okay. Well, for example, I am already in the data science directory. That's right. Sorry. You're right. This one. So far, all good. Everybody has an Ibex space, live user. Weird. So everybody has their own data science folder there, the onboarding. You didn't. You couldn't clone it? Okay, so use your home in this case. It doesn't have a /user, so go ahead, use your home. In this case, it should look like something like this. Okay, so the difference was the best practice is like to run it from here, because here you have to start already landed on the parallel system that is specialized for the HPC connections. That's one. You have more space. That's the second. And third, whenever you do pass through your home, thinking that you are having a 5-lane highway going to a 1-lane highway to a 5-lane highway again. In this case, you are already in the parallel system that is connected to the compute nodes by a highway of 5 lanes. So that's the difference. You will ask for the resources there, and if everything is in the Weka and the /user, it's easier for the computer just to put all the data back and forth, back and forth. Ibex. Yes. Yes. Yeah. Yeah, you got it. Yeah, I mean, the real problem here is that your data has to live always in the Weka. When you ask for the resources, it doesn't have to pass through the home. You have to avoid home. That's the trick. In /users /ibex/users your user. Here, yeah. I mean, in this case, let's close this one. Go back here. So you have Ibex users, your user, then put your dataset there. If you're going to use it with more people, probably you have to ask for a private folder that will also live in the same file system, the Weka.io. But all your data is going to live here in the Ibex/user. Yeah. How much stack? 1.5 terabytes. Yeah, home only has 200 gigabytes. That's the thing also. Okay. So if you go, for example, to JavaScripts, templates, basic Slam, and we put this here. We put this here. This is a basic Slam structure. You're asking like you're giving a name, asking, I have one task, I want 4 CPUs in this task, one GPU of the node. The constraint is A100. This here is actually specifying like, I want specifically this type of GPU. You can change it to B100 or just leave it empty. And you can take it out too. And this is still a valid thing. The difference into putting constraints inside or not is that it will give you any GPU without it that is available. Okay? So in theory, if you did the whole thing, JavaScript, templates, basic, batch, basic. And then I submitted my job. And then it's now running. It's that easy. Okay? If you were in the DS reservation, you add here dash reservation equals DS. Is DS training, correct? Yeah. There you go. This one. So the question was, what is reservation? Can benefit from that. I think. Oh, okay. Don't put this happen to their job. How does every Yep. So for this training session, use the DS reservation because that will give you preference to run these jobs. So the next exercise is very simple. Try to now ask for 2 GPUs to modify the basics one and just run it again and see if it goes through or if it gets canceled. You will already see things popping up or populating the folder there. Okay. The part of submitting the job is the same. You use merge. The trick here is you have to edit the basics long script, ask for more resources. Simple, I guess. Okay, good question. Because it's not in the same. You're here in projects, right? Data science, the job scripts, templates, basics long. Maybe if I do it with this one, IDE, data science onboarding, job scripts, templates. Now we're doing multi-GPU. So if we do cat, this one, here's your hint. How is it different from basic? Matter of fact, we can check it with BIMDIF. Basic versus multi. Single no. Okay. Not yet. So if you want to compare, for example, basics long at your right, at your left, sorry. And this is a multi-GPU single node. You can see clearly the difference, right? We're asking for a little more CPUs. We're asking for more GPUs. The constraint is different. Actually, one has constraint, the other one I erased it. And the time is the same. and they're basically doing the same process after. They're loading a module and then running a program. Okay? QO. Yes. Oh, between srun and just plain Python program, right? So srun uses actually the scheduler to actually direct your Python script into the CPUs and GPUs that you actually work with. If you use the plain Python script, you will basically just run it, but without any control, any kind of control. Srun will give you control over the nodes and the processes that you can deploy. Yes. Yeah, I mean, srun will give you more control over the resources. If that's what you want, we will, if you use something that is in the next slices that is distributed training, you need a little bit more fine tune. If you're using other automatic libraries like random forest, you really don't care which one goes to what node. It's about the precision that you want to put into your code. Obviously, if you know how to use srun, it's a very good practice to use it. But okay. So, hey, I run everything here already. Now let's discuss the output. So you can see here that I run this one. I submitted this multi-node GPU Slurm script, and this is the batch number. I have the matching output of that one here. Okay. So we can check it out. What is inside of this? You can copy paste it. And here you can see that we have how many GPUs? 4. Is there a GPU? Yes. We were using CUDA? Yes. This compared to a single one, which is here. You can see the difference again. Now, the first one run in an A100, this one run in a B100. And before we have one GPU, we ran 4 GPUs. And now this number of threads, which is the CPUs that we specified, also change. So we just successfully run two types of different scripts. One that is asking, okay, you have exactly the problem that my friend over there asked me. Like, where are you? Are you in the CPU node, logging node, or in the GPU logging node? So probably that's a CPU node. What you have to add to your is the module load R9 UQ. So if you are in that one, you have to do module load R9 GPU stack before loading the machine learning module. Like this. Into the script. Yeah, if you do basic, you have to put it actually before you load the machine learning module. And then it will go over that CPU stack or GPU stack, and it should run. Okay, for all of you that we already reached that part, you can ask for more resources if you want, because now you know how to do it. Now you can go crazy and say like, okay, let's do 2 nodes with 4 GPUs, whatever you want. That's if you want. If not, you can take a break. And remember, we have these functional commands already. You already use them, all of them. Okay? So you can go crazy and ask for more resources, or we can take a pause for 5 minutes. Is that okay? 5 minutes pause? We're getting coffee anyways. We're not getting coffee. That's the problem. You all not have coffee. You should be an angry man. Yeah. Okay, 5 minutes break. Everybody can get angry because we don't have coffee. Okay, let me check with you. Testing. Okay. All right, guys. So let's resume. So one of the things that many data science need is an IDE to work with. So the premium UI for data science is Jupyter. So in this case, we're going to jump directly into the exercise because we already have a template for that. Okay, something that works with the machine learning model. You will find the script on the launch Jupyter server folder. Okay, now I will come back to this slide, but first, the Jupyter launch has this kind of these two main components. You will see the script has already the S batch that it will tell like, okay, I want 1, 2 GPUs, blah, blah, how many CPUs, memory, the name, the partition. So please check this JavaScript before you launch it because I don't remember if I changed anything. This is why I put the double XG on the memory. And then the second part is basically loading the machine learning module, then establishing the communication from your computer to the supercomputer to the actual computing node. It will print next some orders that you have to follow, some directions, which will be technically the most important thing because it will tell you like, okay, do this SSH in a new terminal. I can connect to the compute node from your computer. Okay, we will check it out right now, and then you will find at the bottom of the output like where is the actual let's say URL direction that you have to copy paste in a web browser to get to the Jupyter and to Ibex. Okay, all right. So let's follow. I will follow this with the actual example. So, okay, first of all, find the launch Jupyter folder. Did you find it already? It's there in the data science folder. Okay. Check launch Jupyter server.sbatch. While you're doing that, I'm going to do it also. Because, for example, here it's very easy to follow. Launch Jupyter server, and then you have launch Jupyter. This is the one that I want you to look at because I don't remember if I changed anything. It seems it's not. Okay, now here it's already done. Good that I didn't change anything. We're asking for minimal resources, basically a small memory, just 1 GPU per node for 30 seconds, 30 minutes. The name is demo. So I will change to the terminal here. What you can do also with SBatch is if you want to change all the things, you're a little bit advanced, you can do this. You can launch from outside the folder, or you can copy from launch Jupyter, launch Jupyter server, batch, one level up. Okay, both are valid, and then you launch the SBatch. It depends on you. So it's already submitted. It's running. You can see that it's already assigned me a small GPU. And then here's the complicated part. When you go all the way down, it produces 2 outs. The first one doesn't have too much information. Okay, this GPU is pinned to this port in the login. Okay, fine. But what you want to see is the error file. In the error file, you will see this command. Okay? So this is the command that I want you to copy. And in a new terminal, you have to paste it. It will again ask you for your user and your password. In this case. Okay, that's about it. That's it, okay? You go back, and now at the bottom, you will see these two URLs. You can take one of them, open a new browser, new window, and you can copy paste it here. Okay, give it a time. And there you have it. So what happened here is that I am already inside. But here, you should see something like this already, right? Mm-hmm. One. Okay. This is, I use Mozilla, I use Brave. Yeah. Some people had problems with some browsers, but the usual advice is change to another one. It should work. Because, for example, I do know about one student that had problems with Chrome. He switched to Safari and it worked. There was some extension or something. Yeah. This is a very good one. So here in the terminal, while your job is running, my job is still running, so it generates two files, one out and one error. If you go to the error file, you will find on the top of that error file this command. So check the error file that has to generate. Then you use cat. That error file has to be on the top. You copy this. You open a new terminal. You paste that. Enter again your credential, your password, and that's it. After doing that, then you have to go again all the way to down to this URL. And you copy paste that to that. So once you have that, you should see in this place your folders, and you can start a terminal here. The difference now, let's blow this up, that now you are inside of the GPU. Before, I am in my learning node. So this now allows you to use the GPU or for whatever purpose you want. So now you can write and test your programs inside of an actual GPU. Okay. So I know it is complicated. I know it's two-step thing. And actually, one of our data scientists came with an idea of doing this in one step. And this is also what you can find in the launch Jupyter server folder. Here you have an instruction launched in one line that you can read it later and then execute this. And you will find this is a modern way in one line to deploy this thing, the same Jupyter lab that we just deployed. Okay? That's your homework. So there is a better way? Yes, here it is. Up to you to read it and use it. Okay? Now that you're inside of the GPU, now you can start doing stuff. But you can check if you're in a GPU if you run NVIDIA SMI. Oh. Okay? And I am inside of an NVIDIA powered GPU. It's a GTX. That was my luck. If you use the large lab reservation, you will get a different one, actual A100. Okay. So, and as you can see, I closed the browser. My job is still running. So that means that I can still connect again and again and again. So if I connect again, it just keeps running. Yeah. New window now in Chrome. Why not? So it will take time again to load it, but there it is. I'm back on it. Okay. So if you want to stop the job at the same time as you want to stop the Jupyter notebook, just log out or shut down. Sorry. It will shut down. Everything is stopped. Then you close it here. And now it's gone. Okay. So the Jupyter notebook is connected to your job. It's running in that moment. We can launch it again. And now with the reservation. Okay, should be it. Now it's running. Again, this is 2 steps. I know. There is a 1 step there. Your homework. Once you have this instruction here, you can copy paste it in a new terminal. It will ask for your password. Okay. Weird. Didn't ask me for my password. But then I can take any of these 2 URLs in a new window, copy paste it, and wait for it to deploy. So in this way, NVIDIA SMI, let's blow it up. Here I have an A100, which is part of the reservation that we were talking about. Okay? Yes. The terminal, or you want to get the terminal? Blank. You have a blank page? Yeah, so I'm here. Okay, so what's next? You can choose to do a terminal, or you can start your own notebook. Either you can actually go here. There should be one up. So this one was launched from inside one of the folders, folder 1, for example. You can create now stuff inside of this. Now, good. Shut down. That's it. Okay. That was very useful. Okay, if you want, you can go over this, which is basically going then and then run one of the notebooks that we have there that I like a lot, as a matter of fact. Not yet. Wait. Oh. Okay. Nice. Now that I did it right, let's put this here. Now here we have a widget that is going to be very interesting. You can see here we have different things that we can help to monitor what you're doing with your GPU. You can, for example, ask for machine resources and then move it over here or over here. You can also monitor your GPU resources and have everything over this place like this. Depends on what you want to do, obviously, but you can monitor all your processes. Now, if we go, for example, to notebooks, we have two notebooks for you that you can check it out. One is this one, which is the introduction. Let's call this out. And this one, I like this one. So why would you like to use GPUs to start with? One of the things is like they're supposed to be faster. If you run the whole thing here, you will see then how it behaves. If you don't know how to run your Jupyter notebook, it's very easy. You just click this, or you can go basically Shift Enter on each of these. Right now, it's loading a file of 4 million rows into the memory. It took 3.1 microseconds. You can see the peak here. Then for this one, which is a GPU, is 2.86 microseconds. And then to do it in a distributed way, it goes back to 3.4, but you can see that it uses different parts of the GPU memory, which is the part of the beauty of the thing. Now, why would you like to monitor your code this way? Very simple, because sometimes you have a lot of different things that you have to load, and you know you're running out of memory. This is a way to be sure that you're not running out of memory. Also, you have to check, do I need more resources or less resources? In this case, we have way much more memory, even if it's a very small memory, it's an overkill. This is important. Why? Because then you can adjust the type of resources you need. And the less you need, the more quicker you will get those resources. Okay? And of course, you can always do things like this type of exercises, which are simple linear regressions, like machine learning, powered by the GPU. And then if you go over this part here, you can see that it barely affects the memory. And of course, this one here is just pretty much just using the CPUs that are attached to the GPU. And it takes barely anything from the system. Well, in this specific notebook, you can go ahead and try to complete it if you want. It's part of your homework if you want to. I also provide the solutions here. So in case you want to check it, like, do I know machine learning or do I do not how to do this? You have the solutions in this notebook, okay? Yes. Where do you find them? They are there in plain sight. If you are here in the data science folder, you go to notebook folder, they are all there and more. Okay? So this is here in the data science. This one died. Okay. So you're in the data science onboarding here, in working directory. You go to notebooks. And here they are. Yeah. So we wait for everybody to have a Jupyter notebook able and ready. What's up? The GPU utilization memory? The second. I think it's the DRAM. Because down you have, for example, the GPU memory, the RAM memory, against the complete memory of the node, of the whole CPU-GPU combination. Yeah, pretty much. If you use the reservation, this job will be is A100. Yes. Very much, yes. It goes to 70 something probably because it's taking a little bit for the rendering of the Jupyter notebook. Yes. Okay. So Jupyter notebook has widgets. So you have the widget here. These are all the widgets, for example, but then you can do machine resources here, and you can put it anywhere where you want. You're interested in the GPU resources, you push here, and then you pass it wherever you feel comfortable with. Here, for example, this one can be put here. Depending on your monitor, depending on how you read things, you can move all these widgets around. So this looks like should belong over here. And then if you want to continue, you can do this. Yeah. I import it first. There you are. You see how small it took of memory? Oh, this is an overkill, obviously, for this kind of notebook, but still. This is part of the beauty of doing software development, where you adjust whatever you need. for example, you can run this one too. Yeah. We have had a lot of recent problems for Windows users. Okay. Yeah, Git bash probably is a better option right now. The login. Oh, external. Git bash. Yes. Okay. So while at it, I'm going to show you the router, basically of Jupyter Lab, which is called Code Server. Code Server is pretty much VS Code, but open source. So we do have basically the same type of script that launches VS Code is pretty much the same story. You have to do the exact same steps, and I will show you. So this exercise, if you want to do it, is basically the same, but is now instead of the launch Jupyter server, is launch code server folder is over there. So give me a second, and I will show it to you. So we are here, correct? Launch code server has this script here. And as always, you start saying like, I want this, for example, for my job to run. Then it sets up all the things that are going to communicate with your computer to the login node. I'm going to basically load the same machine learning model because it's where everything is going to play in the same directions. And then I will have to do the SSH minus L that I did the thing exactly before that. Let's do SBatch, launch, code server, launch code server, Ibex. Now, I have a name here, which I know this is a Jupyter lab, and this is the code server. Oh, let's wait for it. Now, again, I go to the error file here, cat. I have this command here, I have to copy paste in a new terminal. give my password. There it is. Go back and copy paste this local host. And then a new window. You copy paste this. And you wait for it. Now the thing with VS Code is like you can change the way it looks, also in the Jupyter Lab. But the navigation is a little bit different. Because if you go like open folder, you can go to anywhere where you want. Kind of it doesn't respect where you were. So to go to the same place, you can just go there, and here it is. Pretty much, it's the same look as VS Code. It's different from Jupyter Lab because it has, instead of widgets, it has other applications. This will not allow you to use, for example, that MB dashboard that I showed with the Jupyter Lab, for example. That's one drawback. But you can use another stuff here that if you have a thing for VS Code, you can use this one. It also comes with the source control that VS Code has for GitHub. But you can pretty much run whatever you want here again on the notebooks. If we go, I don't know, this one, you can go and run everything. Obviously, you have to install other things, but at the end of the day, what we want to show you is that you have other options to do.
Yeah. So, on clarification.
Yeah. It is.
You are at, and that's the that should be login.
Yeah.
Login, you want to login on something.
Yeah, here, like just to go over. Remember, the terminal will tell you where you are. This is inside of a complete node. Now, this is the closer feeling you have to your own personal computers. Now you can start working in a prototype, and it's with the resource that you're asking. Okay? But this is a choice. This is a style choice. Where do you want to work? In this VS Code or in Jupyter Lab? Up to you. All right? So let's go ahead. Oh, yeah. We're almost there. Yes. Okay, for Python, if you go to the starting pack, you will find that we advise to use Conda to create your Conda environments. And then you can say whatever you want inside. And you don't have to work for us. Because we have a lot of, for example, tickets that, can you please install this package? Most packages can be found in Conda, and it's like you create your Conda environment, install whatever you want there, and then wait for anyone to install it for you. Also, you can install, for example, Jupyter Lab and all the different thinkers, all the different things that you want inside over there. and you run it with this, and instead of using the machine learning model, you use a command model. And then if you're using the machine learning module, it will block you. Because you have to do, I think, is pip install -u to do your user, but that's not practical. It's better to do the whole environment, and then you have everything contained in one place, and you don't have to depend on other things. Yes, but thank you for bringing it out, because right now, what's up? Nothing. Okay, so because one of the things that we were going to talk about now is containers. Okay, so we have many tickets about, hey, I don't have this library on Ibex. I don't have this program on Ibex. Can you install it, please? Usually we don't say no, but it's like you can install it yourself. You can run it with us. You know, like you can be super independent of us. We can lend you the machine, and you manage your software. And it's like, I want the latest, or I need the oldest. And then, especially when you need the oldest or old versions, is when the problem arises. So one of the things that solves that is called containers. So what is a container? Back in my days, when I was young and had hair, there was the virtual machines. All right. So virtual machines for me were a revelation, because it's like, oh, now I can run, I don't know, something Linux inside Windows, or I can run Windows inside Linux. But this method was very heavy. It took a lot on my disk drive, because the virtual machines bring everything with them. So they are big. It's installing basically another OS inside of your computer. Basically like having a partition and having Windows dealing with the Mac OS. Okay, so that was not practical for small applications, like, you know, running stuff like large language models now on the device, or other applications like Snapchat, because you cannot install like the full Linux inside of inside of a mobile, right? Cellular phone doesn't have that much power yet. So one of the things that you can do is basically borrow from the OS. Already the system has some libraries, already the system has some specifications that you can leverage. And then you run your application, and you technically say like, okay, you run this as if you were another thing. That's pretty much the idea of containers. Now, what's happening in HPC systems? The difference between you running a container in your computer is like you have access and you can modify whatever you want. In the HPC system, you are not allowed to do that. Okay? But let's take it a little bit slower. So, precisely for that, you probably heard about Docker. Docker is the widespread software for containers all over the world. All applications use Docker, is pretty much everywhere, but that has security issues in the sense that pretty much you can connect everybody to Docker and they can see through your system because it's not transparent. Now, you don't always do that. You don't always want to do that. So for other options for the HPC system, we have Singularity. There is another thing called Postman that hopefully we will get. It's still in the works. But right now, if you want to run a container inside of Ibex or Shaheen, you need to know Singularity. It's very specific, it's very niche, I know, but let's talk about Docker, because it's what everybody knows. Now, Docker is a very simple, it has the idea of being simple. It has a very simple structure. So here is a Docker file. And if you know a little bit about Linux, it basically does many of the instructions of Linux. And you have to put in capital what you want to do before what you actually want to run. So this structure is everywhere in Docker, okay? It's supposed to be like that. Like, okay, tell the machine in a human readable way what you want to do. So this example here is going to actually generate what we call an image. And then you can export to different computers. And if I do it in my Mac, it should be able to run in a Windows machine or a Linux machine as long as they have Docker. Okay, that's the idea of making it like that. Like if you want to install any library or Python that you want, you encapsulate an image and you move it, and let's say your computer breaks down, but you still have your image. Your new computer is a Mac, and you were using Windows. You install Docker, and it still runs as the same. That's beautiful. That's supposed to be like a really good solution. Pretty straightforward, right? And then we have the steps. How do you create a container? Okay, yesterday I had this question. What is an image and what is a container, right? The image is the actual file that has the libraries and the instructions that you're going to use. The container is the virtualization of that. Is what you are going to work with at the end of the day. Basically the interface. Okay? So it has steps that are pretty similar to what we do with configuration, because you build the image, you commit the image, meaning that any change you have to log it, and then you push the image into certain registry, which is Docker Hub. So it's pretty similar to what people already does with GitHub. It's the same. Any change that you do in your code, you commit it, so you make a label like I changed my code here, and then you push it to your own GitHub repository. And this is how you control version. Then the difference is like anyone can pull your image and execute it, and it should run as long as they have Docker. Okay? So again, the motivation of this, basically to allow you to install whatever you want without you needing us to intervene too much. Also, the motivation should be reproducibility, because it's like, is your sign reproducible? How do you secure reproducibility of your research? We know, at least if you're in academia, you know, like you can take probably a paper from 2 years back and it has some software, but they don't tell you what it ran on, you get another result. Right? So Docker is a way to also put numbers on that and say, like, you're going to run this program with this that I'm giving you, and it will give you this number. Okay? So part of that is like, now you can do inside of your container whatever you want. You want to put install, I don't know, all Facebook research repositories. You can do that. It will be huge, but you can do this kind of stuff. Okay? So there is this exercise. We're going to run a container. I'm not going to put you through the pain of building one right now, but if you need, you have also the following Thursday is going to be Containers 101, where you can learn a little bit how to build your own containers, right? But now I want you to copy this file from that folder. We have that folder that is a temporary folder that you can access. So in there should be this horror.zip file, okay? And please copy it inside of the containers folder that you should find also in the data science folder, okay? Okay, you find that? But just to let you know, we have, for example, this kind of temporary folders when you have to share data with us. And then we can create a folder in this kind of partition, temporary partition for you. You put the data there, then maybe we can. Permission denied. Let me change that. EMP, KBL, AI. Okay. But this should be enough, right? I hope.
Where did you?
Over there. Here you will have actually, we'll find these two images we will use for the next exercise, this one. But right now, please copy this one. You put it in the containers folder. Yes. Oh, so this is Linux. We do have a shell shop. So copy, you put the whole path. What is not showing? Oh, little detail. Thank you for that clarification. Okay, so going back. In working directory, you should be working on hidden containers, okay? Right? Yes. No? One. That's weird. Okay. Yeah. KBL AI. So should I add minus O? Yeah, I mean, it's like I enable like full.
So can you please check if you are on login node like 10 minus have to be on there. Okay. On that? Yes.
Yeah, that one. Okay.
Let me put it.
Okay. Yeah, 7 should be all right. So back there, for you were asking is CP, then the whole path slash horobot if space dot enter. And that is giving trouble for some of you. Am I right? I mean, I know you have problems with that one. It worked? Did it work for you? Problems? Same problem. Okay. Give us a second, we will move that somewhere else. Yeah, yeah. Uh-huh. Okay, so in my case, what I usually do with VS Code is like I connect to the login node like this, and I write whatever code I have here, right? And in my terminal, I run srun like this. I ask for a GPU, and then I can run my code here. There is one, but it depends if you're prototyping or not. The best way is to enter the GPU to start prototyping and not stop. But it's a matter of how quick is your test. I use this for testing things that is going to last for less than 5 minutes, for example. Okay, like this. Go ahead.
Do that, exactly that.
I got one. Now, those who have problems. No, he was successful. Good. All good? No. The zip file. Yeah, we need don't horrible zip files, and that's it. Okay. So in this case, going to the exercise, we have this single node slurm job. Okay. So this here will allow you to run, as always, with some specifications, a singularity container. So the building of a singularity container is a subject for another workshop. This right now will allow you to use this singularity image that we call HORIBOT-SIF. It will use MPI run. What's that? MPI run basically is a parallel way. It will use parallelization of a task. All right, so in each GPU, there will be one task running. And then it will execute from that image, the Python that is inside of that image, and it will use this Python synthetic benchmark file that we have outside of the image. Okay? Is a complicated way to do it at first? Yes, I know. The first part is the one that you have to understand. You're invoking Singularity just like you will invoke Docker. And you will actually tell him, Singularity execute using NVIDIA enable a characteristic, which is the /MB, and execute that image. From that image, use that Python inside of that image, and then run my program that is called like that with whatever I want outside. Okay? This is how you read this thing. So please launch that. Let's do it with the reservation, for example, sbatch dash reservation. You're going to miss the reservation. Okay? So I have a bunch right now running. The last one is this guy, HORIBOT. Okay? And the last thing that is doing is this log, one node log. Okay? Start warming up. So what you're doing here with this synthetic benchmark is that it's actually loading images into the GPU for each second, okay, using PyTorch. And then it will start one with TensorFlow, okay? And you can see running super fast, 3,000, more than 3,000 images over a matter of seconds, okay? This is what it feels like to run something in a computer super powerful. And then you have the same thing for TensorFlow, okay? Obviously, this code depends on how much you know each of those frameworks. This is just a demo of how you load things super quick into the GPU. And then it's training a model, okay? But the headache of everyone in AI is how do I input so much data into the memory that it doesn't die? This is one way. And you see, loading super fast. 800 images per second in the GPU. You have 4. So you can go like this with your images. Okay? Nice. So I hope you all run this example. Was anybody unable to run the example? You? You were able. Okay. You too? No. You still have problem with the permissions? Really? The PI. Oh my God. Okay. I understand. Sorry for that one. Yeah. Enjoy the video. Okay. Okay, so far so good. Yeah. Okay, so pretty much, except for those that doesn't have an assigned PI, sorry, you were not able to run this, but pretty much everybody okay with this demo? You have problems? Same problem, PI. Okay, sorry. Is generating a log file at the end? Is it pending? Okay, it's pending. Did you use the reservation? On the submission. On the submission. Okay. All right. So here is the thing. Why did I make you use horrible? What the hell is horrible? So what people wants to do in a supercomputer is to use as many resources as they can, right? Why? Because it has to go faster in theory. So this is what we're going to call a scale out. Well, it's not exactly demos because it's just one demo. For this one, we will use 2 things. One that is PyTorch distributed, which is a very popular now because PyTorch is very popular and is very flexible. It has basically the same properties. It will allow you to use your code in different nodes. Okay. Horrible is also the same story. The thing with horrible is more comprehensive. It includes 3 of the main frameworks: PyTorch, TensorFlow, and MXNet. Thank you. So horrible is more broad in that sense, but that doesn't mean that you cannot use both of them for whatever you want. Okay. So the scaling thing is what you see here, right? If I had to train some kind of machine learning algorithm and I have to wait for 10 hours in one GPU, what happens if I just, put 2 GPUs on it, or 4 GPUs, or 8 GPUs? In the ideal world, this is what it happens, right? It decays, at least linearly. The time that I have to put or wait for my result, it will be less and less and less, in theory, because I'm just putting more and more work. Well, not always the case. we have something that is called strong scaling. Now, in the strong scaling, the definition is that it measures how the performance of a parallel algorithm improves as the number of processes is increased while keeping the problem size fixed. So what does that mean? That if I have my database and I just keep throwing CPU side or GPU side, my time will fall or go linearly, or in this case, exponentially, lower and lower and lower. Meaning, for example, training GPT, it takes a lot of resources, which in theory, you need a bigger and bigger supercomputer to train it, right? That's the idea. You have a fixed side problem, and then you just throw resources at it until it says, okay, here it is, and you know. Okay? And of course, you can use large part sizes, which means like how much information you're feeding to the GPU. But what we usually have to face, which is a very painful one, is this, the weak scaling. Meaning that your code is going to deal with something that is not exactly fixed in size, and you can push for a lot of information inside of the GPU, and still you have a very different scaling. If you compare this plot to the other plot that we see before, you can see that the reduction in time is not that dramatic. In this case, you can pass from 10 hours again all the way to 2, but it will keep the batch size in the same number. And you're trying to fit the same information to the GPU as much as you increase the GPU. Go back.
So generally speaking, that process while how efficient drops like very that is that size the globe. Right? That's the problem. Solve with your mode. What remains the same? Size and size. You just
Different GPUs.
the more you distribute it, the less work the GPU gets. Calling, asking for patches. Parallel efficiency.
Down.
That's a bad way of doing it. Right? Ideal world has been top scaling, but increase the size, global batch size, by keeping the batch size per GPU. Right? So your global batch size eventually batch size multiplied by
The number of GPUs.
In other words, you will see the term micro batch size inside that kind of term for every GPU. Global batch size or the training batch. That's actually the parallel efficiency. Not only the function, it is also a function of the hardware, right? So this hardware is very good. That's why we are going to deep dive into it.
Tomorrow is distributed?
Yeah.
Okay, yes, then yes.
Tomorrow is unit training. We are not only going to talk about other
Yeah, these are concepts anyway. Okay, so going head to head, PyTorch versus Horovod in this kind of data sets. This data set that you see, ImageNet, is important historically because this is what people say that it started the neural network evolution because it had like 1,000 different images, 1,000 different classes of images. Meaning they have a lot of photographs for everything in the world, and then it's like dog, cat, Okay. So as you can see, it can take a lot of time using PyTorch DDP, but still it's more flexible than using Horobot. And the reason why we're using Horobot as a singularity image is because it's a really difficult framework to install. Like, it's not something that you can do with pip install, or it's like an Excel. Is complicated. So the Horobot people, what they do was to containerize it and like, okay, now you run it, whatever you want. And still, the performance is very good, right? Okay, so the next exercise is precisely that. We want to run a multi-node Horobot run. Now you have to copy that one. This one is a different Horobot image because this one is blessed by Mohsin, as a matter of fact. This image you can find it in the KRCCL image repository in Jupyter, and then you can convert it to the singularity. We will see that in the workshop of the of containers. But then please just copy this into your container folder again. And submit the job of multi-node Horobot. You will see that also it generates 2 log files. And then you can catch what they're doing using tail -f. And you can compare like one node versus multi-node. And as a matter of fact, right now, the script that we have, the multi-node Horobot flow, has very minimal resources attached to it. It was just, I think, 2 nodes and like 2 GPUs, something like that. It's really, really, really small number of GPUs.
Running yourself.
Yeah. For offense that has the PI-less. So I'm going to cheat a little bit because I already have that here, like Horobot GPU. Now, if we see the multi-node, you can see that I am just asking for 2 nodes and 2 GPUs per node. This is actually a small resource because I don't want to basically be stuck in the queue. I will do that. Will not modify it. Just do the reservation thing. Okay. You can see here that I just changed the image name here. Is basically the same kind of instructions. It should be running. Now it's here pending. I should cancel some of those. For example, this one is the launch. This one is this one. And this one that says bash is the one that I initiated here. It's still running. But this one I can exit, is done. Then I cancel these other 2. Now, a little bit of luck. It is running. Okay, check it out. It's telling me that is starting with that TensorFlow, but still nothing. Yeah. Unless something went wrong.
How many people are
1, 2.
developing? Very question. How many people
1, 2. Yeah.
Are you guys developing node for using?
Or a bunch of different programs.
So, else? That's the major thing. Software environment covering you for your model. At a stage when software that's where us or first and then question. Answer to that. Something yes or in case of environment structure. I can tell you additional is we have documentation on the part of it. Then create a conda environment as a base environment. That is also true. I don't know if that also changed.
Yep.
This already had in like right. But in Kubernetes, diodes will I can accept. But then for CUDA from 11. That's where containers may or may not have. Because people may have to at this very moment ask people jobs or building that is that happens and then every cell push you hopefully. That's the best way. The other by Pythonic workload better in yes, but there are few for
I don't know. The output is not. Ah, here it is.
yes, it writes in the
Yeah. Okay. There it is. Warming up. We will see. Okay. If you reach this part of this downward, yeah. Then the next exercise is considered with PyTorch DDP. Okay. Now this can take a little bit more time. let's go over here. The PyTorch DDP example is here in Torch DDP. So for this one, you don't have to copy anything. So if you go to Torch DDP, you probably can load the machine learning model and run this download file. It creates a directory with all the data that you need for running this one. Yeah. And then we can check that's multi-node, multi-GPUs run. Does this should be less time, as a matter of fact. We submit the jobs and then we check the log files. Pretty much the same structure as before, right? So we go on screen. You go to this directory here, HDP. Okay. So in this case, you can load the machine learning model. Is there. There should be no problem for this one. But in my case, I cheated because I already have them there. This is what you want to do, basically. Go inside of Torch GDP, load the machine learning module, run this one, download data. Okay? And let's check it out. Let's see this example. Now, in this example, we are actually asking for 2 nodes and for 8 GPUs. Okay? We have 2 nodes here, 4 GPUs. As you can see, the order of these, how do we say it? This S batch hashtag, they don't affect. They just are there and slowly will written, and then it will say, okay, I know you're asking for 2 nodes, and you need 8 GPUs. Okay. As long as you put that in any order, as long as it recognizes it, and then it will give it to you. So once you have the data there, then we can go over the whole code. We need to take into account who is going to be the master node for this, basically who is going to be the coordinator of the distribution. And then it will run basically in a for loop, going in each of the different nodes, executing basically the process that we want to execute, which is this Python that we have here. It's called train EDP. So we can do that with dispatch. Where is the dispatch that you want? Oh, let's be greedy. So while both things run, so by the way, it might come to you also then like, how many jobs can I put in Ibex, right? Like what's the maximum numbers of jobs that I can put on the queue? That's a very good question, but it's constrained as how many GPUs per user we can give you and how many CPUs per user we can give you. So there is a number of that. Okay, if you put 5 that uses basically a quarter of Ibex, obviously you will not get the resources. But depending on how many CPUs you ask and how many GPUs you have asked, it will be a number of jobs. And as I remember on the top of my head, like you can put 2,000 jobs in the queue. That's the basic limit because it's going to be like a super long queue that nobody knows when it's going to end. But okay. So one is not running. Let's kill one of those. Cancel. Let's kill the one from Horvath. Now, hopefully, those are going to get assigned to me. Nine, 3, 3. So there is an out here already. Let's check it out. Cat. A bunch of warnings. Nice. Because it's running. Okay. Fair enough. The thing with warning is like in development, we like to just not put attention on it. But now, actually here, it's running. SQ minus. And then we can just monitor. Oh, I monitored too late. It already finished. So in this case, we were training a torch minus, let's say, 15. And you can see that each epoch was super quick. Basically 10,000 image in about, okay, 39 seconds. That was quick. The whole training of my very succinct and very small touch code, it was done in less than a minute. So if I were using only one GPU, this will take pretty much 10 times more. Okay, so this is one of the ways that you can speed up the training of your code, as long as you know how to input the DDP. This one or homework will take you to another level of how fast you can train neural networks, for example. Yes, go ahead, please.
So, quick question for developing more. When would you need?
Yes.
That's the most. What would be your one of the running it on
Yeah.
these are three different ones, right? First, that takes it one up, right? It's hyperparameters, but element itself is a element. So generally speaking, have trials. The trials you may have like multi-level problem.
Mhm.
There is a question of management, project management. Hard because you are the one who is doing it. But all of a sudden you share it with someone else. Problem, right? Collaboration. On 30th of December, we are trying to solve that problem.
Yeah.
Right? We're trying to run something called hyperparameter on platforms. There are tools for it. One of the tools.
Right.
How do you Ibex? Get ready how to do hyperparameter. Then, once we are very comfortable with it,
Yep. All right. So this is the end. Congratulations, you survived. So,
yeah, so timer off.
yeah. You should complain. There was no coffee.
Any questions?
Yes, there was no coffee. We don't know if there will going to be coffee next time. Yeah.
So
okay.
That is there.
Mm-hmm.
We can come to the next. You can ask this question. But try it out what you have. Talk to your PIs for those who have the allocation. And a survey of probably all the training. Data.
Hopefully. Yes.
Here, these are on the